started? Any questions, guys, on homework or anything else? Yeah?
Yeah, let's say that. So, question was on homework last night, kind of a long question, so I'm just gonna read off the actual important parts.
Okay.
It says, construct a 98% confidence interval estimate of the mean, and then it gives us, basically a list of 7 numbers.
So I'm just gonna summarize, you have 7 numbers here, and then we'll talk about
Yeah.
the general approach as to what you would do. Okay?
So do you want to list some?
I know, that's fine. So basically, you're just given that you need a confidence level of 98% in this estimate of the mean. And basically, you're told that you have a sample of 7 numbers, and from this sample of 7 numbers, you want to estimate what the true mean is for the whole population that the sample is taken from. So basically, we talked last time about how there's a formula to estimate the population mean, and the formula is this formula. So this is the true mean for the population you're trying to find. X bar is the mean for just the sample. So what you would do is punch in these 7 numbers in your calculator, and your calculator will give you a sample mean, and it will give you a sample standard deviation. So this is from your calculator that you'll get from entering these 7 numbers. And so that X bar will go here in the formula, and the S will go here in the formula. And then N is the sample size that you'll have here, which is 7. So you have everything that you need except for T, and we talked about how to find T last time, which is this T-score is based solely on the confidence level that's given. So you go to your chart, and you look up, remember the chart, first column is degrees of freedom, which is n minus 1. So in this case, n is 7, n minus 1 will be 6, so go to 6 degrees of freedom. And then go over to the column headers. The first row will be area 1 tail that you specify versus area 2 tails in the next row.
So 1 tail would be 0.01, for 2 would be 0.02, and 6 on that is 3.143.
Okay, so let's build up to that. So you can visualize what we're doing here by drawing this distribution. Remember, since we're estimating the true mean, this distribution ends up being a t-distribution. And again, the reason for that is that the variable you're finding the distribution of is our sample means here. But unlike in the central limit theorem, where a distribution of sample means will be a bell curve, this is a t-distribution because sigma, the population standard deviation, is unknown here. So notice that all you're given are the sample numbers, you're not given any population numbers. So the central limit theorem assumes that you know the population standard deviation, and if you don't, the distribution is not a bell curve, it's this t-distribution that we talked about last time. So in the t-distribution, this confidence level corresponds to the area in the middle around the peak, around the mean. So this area in the middle turns out to be the 98%. And these 2 boundaries that separate out the middle area are called the tails of the distribution. So in this distribution, the 2 tails combined add up to how much?
2 tails combined would be 2%.
Yeah, 2 tails would be 2. But if you look at each 1 tail at a time, individually, how much would each tail be?
1%.
Yeah, each tail would just be half of 2%, which is 1%. So then, in the table, you would look up either area 1 tail as 1%, or area 2 tails as 2%, and you'll notice in the table it will be the exact same column. So then you would use that column, and then meet, or intercept this row of 6 degrees of freedom, and then this would be your answer. And what was the answer?
For that one, it is 3.143. 143. 3.143.
Okay. So then now we have all the numbers we need. The t-score here ends up being 3.143. So at this point, you just punch everything.
I can swear, gun to my head, that I did exactly this. It works with 2 questions, following this one, but it did not work with this one.
Okay.
I, on my life, did exactly this 3 times.
So do you want to do the exact numbers together?
If you could, please.
Sure,
Yes.
sure.
I'm really curious on how I got this wrong.
Okay. Let's tackle this together. Okay, so I'll do the 7 numbers.
Alright, so 7 numbers. We have 0.52, or 0.53, sorry.
0.53.
0.72, 0.1, 0.92, 1.35, 0.55, and 0.95.
Okay, so anybody with a calculator? Go and enter these 7 numbers in, and let's see what we get for the sample mean x bar and x.
Alright, so sample mean that I got for the 4th time now is 0.731.
0.731. And what standard deviation did you get for the 4th time?
So in this situation, to find standard deviation, could we use the original n times p formula to?
No. So use the number that came straight from the same list of stat variables in your calculator. It'll be somewhere next to x bar, so it'll just be s.
I think it was 0.366. I need to get out.
Okay.
So.
I showed 0.395.
I agree with
it's
395.
0.395.
0.3 something, so yeah.
Okay. So let me see the screen you calculator.
No, say SX.
That's it.
Yeah, SX is for your sample, not the sigma X.
Not the
which is
sigma.
The difference.
Okay, so S will be 0.395, X bar will be 0.731. And so let's punch this in, and let's punch in the thing after the plus or minus first, or the margin of error. So that would be 3.143 times 0.395 divided by the square root of 7. That was the whole margin of error.
So it goes 469,237,224, but we're just using the last 3 because it's the same way the homework did it.
Okay.
We just used rounded 3 decimal spots.
Okay, and then so you take 0.731 and then add and subtract this margin of error. So the lower bound will be 0.731 minus the 0.4692.
0.2618.
Okay, this lower bound and the upper bound will be 0.12. 1.2.
Yes.
So should that be the right answer?
According to this, yes, according to the Pearson thing it was, so I guess I must have just like accidentally pressed a wrong number somewhere in here, 3 times in a row, probably all different spots.
Okay, that's okay, that happens.
Royally pisses me off, cause I spent 30 minutes on this one and I
Yeah.
didn't get it right.
Bless you, I spent 3 hours cussing at my computer last night, so yes, I hear you.
Yeah.
So when you go to your data and you're looking at it,
Yeah, it's the SX, the one we gotta use, cause I kept using the sigma X symbol and Y.
So I might have looked at one and typed in the other, entirely possible, so, yeah, you are correct.
Alright,
And I figured out the other 2 within seconds, like the
Yeah.
following 2 questions, so,
Okay. And once you can do this, the following one is like,
yeah.
alright, good, any other questions? Okay. Let's continue then. So, as you guys know, there's a test coming up.
Yeah.
So test 2 will be open after class today and it will be due before class starts on Monday. So, due at 1:30 Monday. And you'll have 3 hours for it. Any continuous 3-hour stretch that you have, you can take it. Again, it's parked through honor lock. So it'll be open book. So this time around, I'm allowing notes, so it'll be open notes. So I know it sounds like a huge crutch, but one of the reasons that I normally shy away from it is it sounds like more of a crutch than it is. And students often spend the time they should be studying to learn and understand the material, they often spend it constructing the perfect set of notes. Or compiling the perfect set of notes so that they have this perfect comfort blanket around them. But again, try to use this as a last resort. Spend your time studying and actually trying to understand the material. And again, if I were you guys, I would go back to the homework questions and make sure that I could do the homework questions unassisted. It's very tempting while you're doing the homework to just press on help me solve this and not really think about what you're doing. But this time around when you're studying, be sure to be able to know how to do the questions unassisted. And then after you're done studying, if you feel like you need more practice, there's extra practice problems that is under files. You might have discovered this last time. So under files, you'll see extra practice for test 2. Again, this is meant as giving you more practice above and beyond what you've already seen to help you reinforce the material. It's not meant to be like a template for the actual test. So don't expect this to be like a study guide in the traditional sense where you do this and that's all you need to do to study for the test. So again, this is just extra practice. This should be after you've already studied the homework questions and know how to go. Any questions? Okay, and again, you're allowed to use any calculator except for anything with Wi-Fi capability. All right, any questions, guys? Okay, so test 2 will cover from chapters 5 to 7, so everything we've done since chapter 1, or since unit 1. So we're just about done talking about all the material for test two. The only thing left is one section, which is section 7.3. This will be relatively straightforward. This will take about 10 minutes, and then the rest will just be review. All right, let's get to it. So in the past couple classes, we've been talking about confidence intervals. So the whole point of a confidence interval is you want to estimate some number about the whole population. If you had access to all the data in the population, like the country, then it would be easy. Like if you wanted to find a true population mean, if you wanted to find a true population proportion of success, you would go through every data point and see whether that data point represents success or not. If it is, count it up, and then divide by the total number. That would be a proportion of success. That's if you had access to all the data points, then it would be easy, but not feasible, but it would be easy. And if you had access to all the population data points, you could also find the population mean. That would be easy too if you had access to all the population data points. You go through each data point, take its value and add it to the next value, add it to the next value, and then divide by all the values to get the mean. But the issue is, we don't have access to all the population data points, and instead we have to resort to a much smaller data set, which we've been calling the sample. And we're going to assume that we have a good sample, meaning that it's random, meaning that it's adequate size. And then from that sample, we're going to use statistics to estimate or make a conclusion about what the true number actually is. So, if we're trying to find a proportion of success, we said that the statistics that we use will be a formula that represents a confidence interval. So the formula for a population proportion of success, we said it was simply this formula. So this is how you estimate the true population proportion of success given a sample. And likewise, if you have a sample and you want to find the true population mean of all the values, then there's another formula. Oops, this is wrong. So that's if you wanted to find the population mean, that's another formula. And the formula that you use depends on the type of measurement that you're trying to estimate for the population. So conceptually, if you're trying to estimate a proportion of success for the population, you use the first formula. If you're trying to estimate a population mean, I have an extra word of here. So if you're trying to estimate a population mean, then you use the second formula. Any questions so far? So that's review. So today we'll talk about a third type of number that you might be interested in estimating for the population. And this is if you wanted to find the true standard deviation or variance. So remember the standard deviation for the population is notated by the symbol sigma. And then the variance is just the standard deviation squared, so that'll be sigma squared. So it turns out that the relationship, or the formula to find the true population variance is as follows. Okay, so again, this is gonna look hideous the first time you see it, but it won't be so bad as we talk about it. So what this is saying is that sigma squared, the true population standard deviation squared, or the variance squared, or just the variance, is between these two numbers, where the left number is n minus one, the sample size, minus one, times s squared, the sample standard deviation squared, divided by this new symbol that we read as chi-square right. And then you notice that on the right hand side, it's basically almost exact in the symbols, except for the bottom symbol. So it's still n minus one, the quantity times s squared, and then divided by, this is chi-square right, chi-square left. So let's put this in the context for an example of when we would ever want to use this formula. So let's say that for your next job, you're head of quality control at an electronics company, for example. And let's say that your job is to make sure that the devices that you're inspecting are up to spec. So let's say that the specifications on this device are that the output voltage on the device needs to be 12 volts. So every device, it should be outputting 12 volts. But of course, this is real life, and not every device is not going to be exactly 12 volts. So let's say that you look at devices. So you have this sample of 50 devices randomly chosen from the factory. And even though the specified output voltage is 12 volts, you're going to have variation around that. So let's say one device will be 11.97 volts, one will be 12.02 volts, and so on. So you have this. So every device is around 12 volts, but not exactly 12 volts necessarily. So let's say that you enter these 50 numbers in your calculator, and again, your calculator will give you the summary statistics, which are the sample mean and the sample standard deviation. So let's say that the sample mean is some number, let's say 12.03, and the sample standard deviation is, let's say, 0.06. Okay, so as head of quality control, one way to quantify that you have good quality with the devices and they're all a good variation around the actual specification of 12 volts is a good quantification of that is to look at the standard deviation. So the standard deviation tells you how much average spread there is around this number 12 volts. So the smaller the standard deviation, the better. So the standard deviation that you see for this one sample of 50 devices is 0.06 volts. So normally that would be pretty good, but that's only for these 50 devices. You want to know what the standard deviation is for the entire factory of devices, not just these 50 in the factory. So again, we're trying to estimate some true number about the whole population, not just the sample, the population in this case being the factory. So what we're going to do is use another formula in order to estimate this new type of number representing a standard deviation squared or standard deviation. But the form that it's in now is the standard deviation squared or the variance. Any questions? So then really all we do is just plug in the numbers. So, what would n be in this case? That's the sample size.
50.
Yeah, 50. Yeah, so 50 minus 1. And then S is also given as 0.06. So this will be 0.06. It'll be 0.06, and then we're going to square the result. I'll just and then we'll talk about chi-square right in a little bit. Let's do the same thing on the right. Okay, so now we have all the numbers we need except for the chi-square values on the denominator of instructions. So let's talk about what the chi-square values mean. So anytime you see a chi-square value or chi-square statistic, what this pertains to is a new kind of distribution. So the shape of this distribution ends up being lopsided with a lot of mass on the left. So it's very different from the previous distributions that you see in bell curve or t-distribution. And this distribution usually arises when you're observing a bunch of sample variances. And a function of those sample variances gives rise to this particular shape. So what that means is if you gather a whole bunch of samples and measure the variance on each of the samples, and then construct a distribution of how often you see each of those particular variances, you'll see that for small variances, you have a lot of representation. But for larger variances, you don't have a lot of representation. So that's all that's telling you is that usually when you have a lot of samples, you're gonna have, for the most part, small variances. So you'll have more small variance than you'll have large variance. So that's generally what this distribution is saying. So this is called the chi-square distribution. So as with before, you're given a confidence level. So let's say the confidence level that you're given here is 95%. So just like before, visually, that represents a middle area around the distribution of that value. So 95% here represents this middle area around the distribution. So that leaves out these two extreme areas that we've been calling the tails. So the boundary that is on the left, that separates out the left tail, we call chi-square left. And the boundary on the right that separates out the right tail is chi-square right. Questions? Alright, so the way that we find these two values, we're gonna look it up in the chart. So let's project the chart up, and we'll talk about how to use the chart. Plus 63 in the book. So you'll see that the first column here is degrees of freedom, and the way that you calculate this is the same as when we used the t-score table. So it would be n minus 1. So n in this case is 50, so n minus 1 would be 49. So you're going to go down to 49 degrees of freedom. But you'll see that there is no 49, it goes 40 and then 50. So in general, if a value doesn't exist in the table, we'll use the closest one. So the closest one to 49 will be 50. So we're going to use 50 degrees of freedom. And then we'll go over to the correct column, and let's see what the column headers are saying. So this says area to the right of the critical value. So the critical value is what you're trying to find. The t chi-square values are called critical values. So it's saying if you know the area to the right of the critical value you're trying to find, then you can find that critical value. So for example, if you start with chi-square right, if you know the area to the right of that critical value under the distribution, then you can find that particular critical value. So if this middle area under the distribution is 95%, then how much area is left across both tails combined?
5%.
5%. So that means that the right tail by itself is how much?
2.5%.
2.5%, good. So then, we know that this chi-square value we're trying to find, chi-square right, has a right area of 2.5%. So we're gonna go to the chart and look up right area of 2.5%. So then, So then 2.5% is here, 0.025 would be this column, so that represents the area to the right, the critical value we're looking for. So then you would just go down to the appropriate row. So going down to the appropriate degrees of freedom will be uh,
71.420.
yeah, it should be this value, 71.420. Any questions on these tables so far? So we got one of the chi-square values we're looking for. 71.420, sorry. And then now we're gonna do exactly the same thing and look up the other chi-square value by the same convention of the chart, which is, if we know the area to the right of this critical value, then we can find it. So this critical value has a total right area under the bell curve of how much? Not the bell curve, the chi-square distribution.
2.5%.
Well, 2.5% is over here. This boundary has a total right area.
And so the rest of it is 97.5%.
Okay, very good. So this boundary you're looking for, this chi-square value, has a total area under the chi-square distribution of 95 plus 2.5%, or 97.5%. So then we use the chart again to look up that right area of 97.5% to find this chi-square value.
32.314.
Okay, so we're gonna look up 0.975 as the new right area. So you notice that that's here, 0.975, third column from the left. And then we're gonna go down to the correct degrees of freedom, 50 in this case. Third column from the left, 32.357. Any questions? So one trick I'll share with you guys is notice the first chi-square value we found, which is chi-square right, that had an area to the right of it of 2.5%. So then we go to 2.5%, which ends up being the third column from the right. But then the other chi-square value, we calculated a right area of 97.5%, and that ended up being over here. And you note that it's actually the third column from the left. So it's actually symmetric. So these two corresponding chi-square values will be the same number of columns from their respective sides. So the first one was the third column from the right, so therefore the second one would be the third column from the left. Any questions?
Do we follow the rules of rounding? Like if we get a 45, then do we pick 50 as the degree of freedom?
Yeah, just pick the closest one that you see in the chart
Okay.
to the one you're trying to find. Okay, good. So chi-square left in this case is 32.357, I believe. Okay, so any questions on using the chart, chi-square chart? Actually, let's practice a little bit. Here, the confidence level was given as 95%. Let's say that the confidence level had been given as 90%. Let's look at a picture. So that means the middle area is 90%, which leaves out these two tails. So for simplicity, let's say the degrees of freedom is only 1, so we only have to look at the first, or let's say it's 2. So degrees of freedom is 2, so we look at the second column, which is the first column with all the values in. So if the degrees of freedom is 2, and the confidence level is 90%, let's go ahead and find chi-square right. So we're looking at this row here that's in yellow. So what value would we look to find chi-square right? In other words, how much area is to the right of this chi-square value that we're looking for? This boundary, how much area is to the right of that?
I have 0.0025.
Yeah, so together, those two tails add up to 10%. So that one tail to the right is 5%, half of 10. And so we're gonna look up 5% as a right area. And so you would look up 0.05. So 0.05 ends up being here. And then you go down to your correct degrees of freedom, which we're gonna do 2, which is this first yellow row. So 0.05 there will be 5.991. So chi-square right for 90% confidence will be 5.991. So this is just extra practice using the chart. So in that case, what would chi-square left be? So two ways you can approach it. One is calculate from using the chart. If we know the right area to that critical value, we can find that critical value. So the right area here will be the 90% plus the remaining 5% on the right tail. So 95% total right area. So we're gonna look up 0.95. So 0.95 will be here. And then you go down to 2 degrees of freedom, first yellow row, so 0.103. Okay, any questions? Alright, so the second way that you could have found chi-square left is you look at the value you got for chi-square right before, that ended up being the fourth fourth column from the right, so therefore the other chi-square value that you need to find will be the same number of columns but from the left. So that was the 0.95, and then that was the 0.103. Any questions? Okay, any questions on using this chart? Okay, so now that we use the chart to get those two chi-square values, now we have everything we need to find this confidence interval. So chi-square right in this case was 71.420. Chi-square left was 32.357. And so you notice these values that we get from the chart are the entire chi-square values, you don't square them again. So these are actually this entire chi-square variable. So once we plug everything in, let's go ahead and just simplify. So go ahead and punch in the left, which would be 49 times 0.06 squared, and then divide by 71.420, and see, let's see what number we get.
That's right up to
0.0025. And then that's saying that that left number is less than whatever sigma squared is, and sigma squared is less than, let's do the same thing on the right. So we're gonna do 49 times 0.06 squared divided by 32.357. 0.00
545. Alright, we're just doing 4 digits, it's gonna be 5
Okay, that's. So what this is saying is that the true population standard deviation of all devices in the factory, that standard deviation squared, or the variance, will be between these two numbers, which is 0.0025 and 0.00545. But this is the true variance of all devices in the factory. But what if we just wanted the true standard deviation and not the true variance? So if the true variance is between these two numbers, then the true standard deviation should be between what two numbers?
Between the square root of what you have right there. Going across,
Okay, very good. So take the square root straight across. So if you don't see that right away, if I tell you that some variable x squared is between two numbers 4 and 9, then that means x must be between what? So if x squared is between 4 and 9, then that means x itself must be between what and what?
2 and 3.
So then you take the square root straight across. So the square root of 4 is 2, and the square root of 9 is 3. So if x squared is between 4 and 9, then what must be true is that x has to be between 2 and 3. So same thing here. The variable squared is between these two numbers, so the variable itself is between the square root of those numbers. So you punch in the square root of 0.0025, what do you get?
0.05, and for the other one, it's 0.0738.
Alright, so this is our final conclusion, which says that the true standard deviation of all devices in the factory, not just our 50, is somewhere between 0.05 and 0.07. And that will be true 95% of the time, because 95% is our confidence level that we give. Okay, any questions? Alright, so that's all the material for Unit 2 test. Let's review a little bit. So, yeah.
I wanna lead off with the first question there, so between your central limit theorem, where you're using Z, assuming you have a bell curve, to your Z table, where you're using the sample variance, right? When you go to your T, the difference is because you have a spike in there somewhere where it can be close to but not exact, and you might have a few outliers, and then your key squared distribution, like what specifically, like it is used when you do not have either the mean or your standard deviation known, so that's when you would go to key.
Okay, so basically the question is when you would use each of the three different tables that we talked about. So let's go over that. So in the context of confidence intervals, let's begin in that context. So remember we said that the point of a confidence interval was to estimate some true number about the whole population, and depending on what that number actually represents, you would use one of three formulas. So the first formula is if you're trying to estimate the true population proportion of success, then that has its own formula. And within that formula, the critical value is a z-score. And whenever you see z, you know that the underlying distribution is a bell curve. And the reason it's a bell curve is because the variable that you're trying to estimate is a proportion of success. So a proportion of success, by definition, means a number of successes out of another number of trials. And you can convert that number of successes into proportion by simply dividing by the total. So, but this is a number of successes out of n trials. And because the variable is framed in this way, to find the probability of that variable, it's the probability of a number of successes out of another number of trials, and that's binomial by structure. So this is really a binomial distribution, and the reason it ends up being a bell curve is that almost in all cases, you can fit a bell curve onto a binomial distribution. And so that was the last part of chapter 6, the normal approximation to a binomial distribution. So because this is a binomial distribution, you can fit a bell curve onto it. That's why we have a bell curve. And that's why in the confidence interval formula, to estimate this true proportion of success, we're using a z-score because the underlying distribution is a bell curve. Okay, so the next type of number we want to estimate for the population is the population mean, and that'll have its own formula. And you notice that the critical value here is a t-score, and when you see a t-score, you know the underlying distribution is a t-distribution. So basically, it looks like a bell curve, it's symmetric. The only difference in the shape is it happens to be a little sharper in the peak. But the reason you know that this distribution ends up being a t-distribution is the variable that's involved in this distribution ends up being that you're taking the distribution of sample means, x bar here. So if you take a whole bunch of samples and take the means of those and build a histogram, you'll see this distribution. But recall, we said that if you have a distribution of sample means, usually by the central limit theorem, it should be a bell curve. But that's only if sigma is known. But in this case, if the population standard deviation sigma isn't known, you only have the sample standard deviation known, then you have this t-distribution. And this is what happens in almost all cases in real life, because you don't know population variables in real life. You don't usually know what the standard deviation of the population is. So if you have a distribution of sample means where sigma is unknown, then you have a t-distribution, and that's why this formula uses a t-distribution, because it assumes that you don't know sigma. And that's usually what happens in real life. And remember, the example we gave for this is, let's say you're trying to find the mean IQ for the whole country, and all you have is a sample of IQ scores. Let's say 50 in a sample. And in that sample, you have all the data points for that sample of 50 people. And from those 50 data points, you can find all the summary statistics, like the sample mean, like the sample standard deviation. But you can't find the population variables, you can find the sample variables. So the sample variables here, all you do is punch in the 50 numbers and your calculator will give you the sample variables, the mean and the standard deviation. So let's say the sample mean and the sample standard deviation are given to you. So these are all sample numbers, these aren't population numbers, and you can use those sample numbers directly in this formula. It doesn't assume that you have to know sigma. So when you don't know sigma, we're dealing with a t-distribution. Any questions? So the last case we talked about today was if the number you're trying to estimate represents a measure of variation, like a standard deviation or variance for the population, then that has this relationship. Yeah, and notice that on the left side of the inequality here, in the denominator, you have chi-squared right on the left side of the inequality, and on the right side of the inequality, you have chi-squared left. So that's not a mistake, that's how it should be. And then the critical value here is a chi-square value, so when you see chi-square, you know that you're dealing with a chi-square distribution as the underlying distribution. So chi-square distribution, looks like that. And the variable involved here is you're dealing with a function of sample variances that take on this distribution.
So when we were doing that example problem, when we were looking at the chi chart, and you said that since we do n equals 50 and we do 50 minus 1, n equals 49, And so is it gonna fall under, is it gonna fall to 30 because it's 34 now?
Yeah, so in general, good question, so in general, just pick the closest one. I'm not gonna give you, a test question where the answer is in the middle of two values exactly. So it's gonna be, there's gonna be one value that's closer to the value that you're trying to find. Okay, any other questions? Alright, so the table or the distribution you use depends on the variable involved in the distribution, and the variable involved in the distribution depends on whatever it is that you're actually trying to estimate for the population. Okay, any questions? Okay, so if you guys have any specific questions, we can address those. Otherwise, I'll just do a bird's eye view of what we've done so far, and anything that you want more examples or details on, we can take a detour and talk more about those. So chapter 5, we talked about probability distributions. So one way to represent a probability distribution is just a table of two columns. One column is all the variables for all the values for your particular variable. And the second column is all the probabilities of all the values that your variable could take. So the example that we talked about when we first talked about this is, let's say that you have numbers in a hat. All the possible values of numbers are anywhere from 1, 2, 3, and 4. And then each of those has an arbitrary probability, an arbitrary number of occurrences in the hat. So let's say the 1 is 5% of the time, 2 is 15, 3 is 30% of the time, and 4 is 50. So again, this is an example of a probability distribution representing what number you have in a hat. And each number has a certain probability of occurrence associated with it. And you notice these probabilities are purely arbitrary. There's no rhyme or reason to these probabilities. The only thing is, because you're listing out all the possible values, they have to add up to 100% or 1. So all these probabilities add up to 1. And then we talked about finding the mean and standard deviation. So you should be comfortable, given any probability distribution, to find the mean value of your variable and the standard deviation of that variable. Each one has a formula, but the formula was in the context of helping you understand what the meaning of the mean and standard deviation are, but in practice, you should be comfortable using your calculator. So recall that these are the formulas. Questions so far? Okay. So then the next thing we talk about are binomial probabilities. This is a big one. So we said this applies when you have a probability of exactly some number of successes out of n trials. So exactly just emphasizes that if you have X successes, you must also have the remaining number of non-successes. But don't look for the word exactly, but exactly is implied here. So what makes this concept particularly hard is that it applies to lots of situations. So this could apply to 1,000 seemingly different looking questions, but they're all really the same concept. So for example, if I ask you what's the probability of 10 defective calculators in a batch of 15, given that the defective rate for a calculator is let me do a batch of let's say that the defective rate of calculator is 0.02. So this would be an example of a probability that was binomial, because it fit that structure that we were talking about of exactly some number of successes, where success means defective here, and out of this number of trials or calculators. And then you're given the probability of success or defect for each trial. So as practice, let's go ahead and answer this question together. So remember, a binomial probability was you use the formula n choose x times p to the x times 1 minus p, again minus x. So let's answer this question together. N choose x would be what choose what?
15 choose 10.
Yeah, 15 choose 10. Times p, which is probability of success. In this case, success is defective. Yeah, so that's given, it's 0.02. Raised to the number of successes or defects that you want.
10.
So that'd be 10. Times the probability of non-success or not defects. Which would be 0.98, good. And then raised to the total number of non-defective calculators you want, which is 5. Okay, so this is just an example of a question that fits this structure of being a binomial probability. Probability of some number of successes out of another number of trials. Now, if you end up using this formula as the answer, if that answer were correct, it actually has to assume that 2 things are true. So what 2 assumptions are there?
The first one is that it is only one of 2 outcomes that you can have.
Okay, good. So you're assuming that for each calculator, it meets one of only 2 outcomes, defective or not defective. And that's reasonable here, that would meet that assumption. So 2 outcomes per trial. And then what's the other assumption?
Then it has to be independent trials.
Yeah, good. Independent trials. So again, independent trials, What that means is the probability of success for each trial doesn't change for different trials. So if you have a success in one trial, that doesn't affect the probability of another success in another trial. So for example, if you have one calculator that is defective, having a probability of 0.02, later on, is the probability of another calculator to be defective still 0.02? If it is, then they're independent trials. So this probability of success, defects in this case, needs to be a consistent number for that probability. And remember, this is where the rule of, the 5% rule came in, is, you guys remember the 5% rule? Said that if the sample size is small, and small means less than 5% of the population, let's say less than or equal to, then we can assume independence, i.e. we can use that same probability of success over and over again. So the sample size in this case is what?
15?
Yeah, it's 15, the batch, 15. So if this sample size of 15 is small, meaning that it's much less than the total population size, then we can treat the draws of the samples being independent. And we can use the same probability of 0.02 over and over again in the formula. But this question was left purposely vague, so we don't know what the population size here. But in general, if the population size is large, where the sample is less than 5% of the population size, then you can use this formula because you're assuming independent trials. But if the sample size is not small, if it's large relative to the population size, then you wouldn't be able to use this formula for that use. Okay, so we're assuming independent trials, and related to that is the 5% rule.
Only one has to be true, right?
No, both have to
Both?
be true. Yep. So I'll connect these with an and.
Plugging in those numbers, am I the only one that got this ridiculously large number with an E minus 14?
You plug in these three components, you mean? And what is it you got?
I got 2.77962153 negative 14 exponent.
What was the very last thing that you get?
With the two, fives.
Oh, e to the negative 14. So, in case you don't know, what this means on your calculator is the e means times 10, and then raised to this power. So that means the answer is 2.4 times 10 raised to the negative 14 power. That means that you move the decimal, this number places to the left. So 14 to the left. So that means 13 zeros with a 2. That's an extremely small number. That's virtually 0. Any questions? So that makes sense to this problem because the probability that one single calculator will be defective is only 2% of the time. But you want to know, out of 15 calculators, what's the probability that 10 of them out of 15 will be defective? So that's going to be exceedingly low because each one calculator being defective is only 2% chance happening. And you want 10 calculators to be defective. So essentially, you're just multiplying the small probability times itself lots of times.
Feels like the odds of playing the lotto.
Okay, good. Any questions? So that's binomial probability. The last thing in chapter 5 we talked about is we combined this idea of a probability distribution with a binomial probability so that the concept is a binomial probability distribution. So a binomial probability distribution is a special case of a probability distribution. And a probability distribution is the first thing we talked about in chapter 5. You can represent it with a table of two columns, x and p of x. That's an ordinary probability distribution. But what makes that probability distribution a special case of a binomial probability distribution is if all these probabilities, instead of being arbitrary probabilities, they were calculated using the binomial probability formula. So if all these probabilities end up being binomial probabilities, then this distribution, this probability distribution is called the binomial probability distribution. And so what's an example of when you would have a binomial probability distribution? It's when you have probabilities all in this structure. A probability of this number of successes out of this number of trials. So that would happen if your x variable here represents a number of successes out of another number of trials. If that's the case, then the probability of that variable, or the probability of a number of successes out of another number of trials, are binomial probabilities that you use that formula for. So collectively, this would be a binomial probability distribution. So what's an example of that? I'll just do this. So an example of that is if you have a fair coin that you're flipping. Let's say you flip a fair coin 10 times, and you want to build a probability distribution for all the possible values that you could observe, representing the number of heads out of 10 flips. So x here, let's say, represents the number of heads out of 10 flips. What are all the possible values you could observe representing the number of heads out of 10 flips?
0 to 10.
0 up through 10. All the values between 0 and 10. And then each of those values, the probability for those are calculated as the probability of a number of heads out of 10 flips. So each of those have a binomial probability structure. So because of that, to find any of these probabilities in this table, you would use the binomial probability formula. So therefore, because all these probabilities are binomial probabilities, this distribution, this probability distribution, will be a binomial probability distribution. And once you have a binomial probability distribution, we said that to find mean and the standard deviation end up being very simple formulas. So what's the mean of a binomial probability distribution?
N times P.
Yeah, n times p. So in this case, for a fair coin flipped 10 times, what's n and what's p?
N is 10, P is 0.5.
Okay, so we should be careful here. So n is not necessarily the total number of values for your x variable. N is here the structure of that each particular binomial probability, because each of these, for example, if you do arbitrarily the number 2 here, that would represent the probability of observing 2 heads out of 10 flips. So this binomial probability fits the structure for this binomial probability of the probability of this number of successes or heads out of another number n trials. So the second number, that represents your n. So n is 10 here. And then x is 2. So x and n are the variables that are in each particular binomial probability. So it's the probability of x successes out of n trials. So n is that second number here. So since you have 10 flips, n would be your 10. And then p is the probability of success per trial, and success is defined as you look at an arbitrary binomial probability. It's the probability of X successes out of N trials, so success is heads. So P is the probability of heads per flip. And we know it's a fair coin, so it's gonna be 0.5. So the mean will be 10 times 0.5, which is 5. And then the standard deviation. Simple formula, which is the square root of NP cubed. So,
That should be fine.
yeah, N will be 10, P will be 0.5, and Q will also be 0.5. So whatever that is, it's the square root of the quantity 10 times 0.5 times 0.5.
1.5811.
Any questions?
Are these two formulas specific to binomial probabilities for the mean and standard deviation?
Yes, so only if you have that special case, we have a binomial probability distribution, can you use these two formulas. But remember, if you have any probability distribution, then you can use the more complicated formulas for any probability distribution. So the more complicated formulas, I erased before, but it was something like so these formulas for the mean and standard deviation apply to any probability distribution, versus these apply to only a probability, binomial probability distribution.
And you said those apply to what?
Yeah, these apply to any probability distribution, including a binomial probability distribution. But these apply to only a binomial probability distribution. So, for any probability distribution, we said that to find the mean, you just take the product of each of the rows, and then you add up those products. So that's finding the mean. So in the case of a binomial probability distribution, a special case of a probability distribution, to find the mean, you can actually also do the same thing. Find the product of each of the rows, and then add them all up. And that will give you the exact same answer as n times p, which is 5. Alright, so that's chapter 5. That's probability distributions, binomial probability, and binomial probability distribution. Chapter 6 is all about bell curves.
Normal distribution.
Or normal distributions. Chapter 6 was all the times where we use bell curves, the 3 instances in this class that we use bell curves. The simplest case was when it was given to you that the variable is normally distributed. So the first case is the simplest. It's given that the variable is normally distributed. So, for example, used this example before, but let's say that we're talking about weights of men. And let's say that it's also given that the mean is 180 and standard deviation is 20. And so the question is, find the probability that man's weight is more than 200 pounds. So because we said that if we have a continuous distribution like a bell curve, that we can make an equivalence between probability and area under that bell curve, then we can visualize this as look at the variable involved in the probability you're trying to find, man's weight, and then look at the distribution of that variable. So in this case, it's straightforward because it's told to you that the weights of men are normally distributed. So normally distributed just means bell curve. So you can draw out the bell curve. And you're also given what the parameters of that bell curve are. You're told what the mean is, you're told what the standard deviation is. All you have to do now is locate the value of interest, 200 pounds, on your distribution of that variable. And since you're trying to find the probability that that variable is greater than the number, that reduces to the same answer as the area to the right of that number under the bell curve. So all we have to do now is find the z-score of 200, look up that z-score in the chart. That chart will give you a left area, and because we want a right area, we subtract from 1, and we're done. Any questions? Okay, so this is an example of the first case, which is the most straightforward case. It's given. Let's talk about the second and third cases. So the second case involves the central limit theorem. I'm going to abbreviate it as CLT. Sounds like a sandwich. But an example of this is, let's use the example we talked about before, weights of men. And so let's say that we select a sample of 100 men, and then we weigh all 100 men, and then we find the average weight of those 100 men. So mean weight found. So the question is, what's the probability that that mean weight of the sample is greater than 200 pounds? So the general approach is the same as before, which is you're going to look at this variable you're trying to find the probability of, which represents a mean weight, or the mean value of a sample. That's also called a sample mean for short. And then we need to know what the distribution of that variable looks like. Before, it looked like a bell curve because we were told that that variable, individual man's weight, looked like a bell curve. But in this case, what justification do we have to actually draw a bell curve onto this variable representing a sample mean?
Your number is greater than 30 and it's supposed to be an or for this one, but both apply, and the original set was a bell curve to begin with.
Okay, excellent. So, this is what the central limit theorem says, which is, if you have a distribution of sample means, that distribution will look like a bell curve. And not only that, but we know the mean and standard deviation of this new bell curve. And that's true if, as long as those two assumptions that were mentioned, one of them is met, which is either the sample size is at least 30, which it is here, or if it's not, then the original distribution of individual weights has to look like a bell curve, which it does already. But only one of those has to be true, and it turns out that in this case both of them are true. So the mean is equal to the original population mean of individual values, which is
180.
yeah, 180. But the standard deviation is not the original standard deviation by itself. It's the standard deviation divided by the square root of n, which is the sample size. So the standard deviation ends up being 2 in this case. So now that we've determined that we need to use this idea, the central limit theorem, for this problem, now we get a new bell curve with the correct mean and standard deviation, and so now this turns into a regular old bell curve problem. So now that you have the correct parameters to this bell curve, the approach is the same as before. Find the z-score, look up the area. So the z-score will be, so again, we locate where this number is on the distribution, so 200. And then the probability that the variable is greater means that the area to the right of the bell curve. So just like before, the z-score will be 200 minus 180, but divided by the new standard deviation, which is 2 now, instead of the previous 20. So that tells us the z-score is 20 over 2, which is 10. So now that we have the z-score, we look it up in the table and find the left area and subtract that left area from 1 to find our right area. So this is an example of the central limit theorem, and that has to do when we have a distribution of sample means. Any questions? Okay, so let's say that instead of this original probability of the mean weight of the sample being greater than 200, the question had been, what's the probability that the total weight in the sample was greater than 20,000 pounds. So how would you approach that?
It's only one extra step, and you're taking that and dividing it by your number so that you have a mean that you can use it for everything else.
So very good. So you can convert this variable that you don't know the distribution of, you don't know the shape of a variable that represents the total value in a sample. But you do know what the shape of a variable that represents the sample mean looks like. It's a bell curve. So you can convert this problem into one that you know how to solve. So you can convert a total into an average simply dividing by the sample size. So this is the same as the probability of a sample mean by dividing both sides of that inequality by the sample size, which is 100 in this case. So once you calculate what this is, which ends up being 200, then now you're back to the previous type of problem. I don't know if that's completely clear, I'm getting a lot of silences,
So the only reason I'm giving you silence right now is because in all the homework problems we have, I haven't had to convert or run into this particular type of problem, so I'm trying
Oh,
to
okay,
figure out
okay.
if that is specifically, something that we could expect on one of the exams, or if that's gonna show up in our homework later on, I don't know which.
I'm surprised that hasn't showed up on your homework yet, but it's fair game for the exam. Basically, it just reinforces this idea of the central limit theorem and that you're dealing with a sample mean here, but if you don't have a sample mean, then sometimes it's easy to convert to a situation that you have a sample mean. So if you're given a total, you convert to a sample mean. So, just in case you're not completely clear on that, let me back up a little bit. So, for example, if you have 6 numbers, let's do 5 numbers. And I tell you that if you were to add up the 5 numbers, if you were to find the total, and the total is 30. So the total of the 30 numbers is 30, but what if I were to ask you the mean or the average of those same 5 numbers? What would it be? Could you determine that even though you don't know the individual 5 numbers?
No, but the mean is 6.
Yeah, very good, because the mean is simply whatever the total is, you add up all the numbers, divide by the number of numbers. And even though you don't know the individual 5 numbers, you already have this big piece of information, which is all the numbers add up to 30. So the mean is simply the sum of all the numbers, 30, divided by the number of numbers, which is 5. So the mean here would be 6. Right, so same idea here. If you're trying to find a total relative to this number, 20,000, so if you know what the total is, you can convert that to an average, to a mean. So you simply divide by the number of numbers. So the number of numbers is the sample size. So you're converting a probability involving a total to a probability involving a mean. Okay, any questions? You guys are still quiet.
You can make it more realistic, is like go up and add up all of your scores for your homework and understand by when you divide that by the total, it gives you something representative of the score up there that's going to equal a quarter of your grade. Now you have everyone's attention.
Okay, okay. we can do that together if you guys want, but I think you have to hang it. Okay, so the second idea here to use bell curves was the central limit theorem. When you have a distribution of sample means, it'll be a bell curve, as long as the assumptions are met. So remember, only one of the 2 assumptions has to be met, which is sample size has to be at least 30, which in this case it is, it's 100, or the second assumption is the original distribution of individual values has to be normally distributed. So I'll just say already normally distributed. Okay, any questions? Oh, we're out of time. So, real quick, so the last instance we used bell curves, recall that was fitting a bell curve onto it, and we started talking about that today. In context with the review today. So the third case we use bell curves is normal approximation. To binomial probability distribution. So for example, if you had a 32 question multiple choice tests, 4 choices per question, and you were to randomly guess on all 32 questions, then let's say passing is getting 20 or more questions right. So passing is at least 20 questions right. So the probability of passing or getting at least 20 questions right is that you either get 20 correct, or 21 correct, or 22 correct, all the way up to 32. So probability with or is which rule?
Addition.
Yeah, that's the addition rule, so then you can break up this complicated event into separate events that you find probabilities for that are joined by addition. So, for example, how would you find the first probability, which is the probability of 20 correct out of 32 questions?
32 choose 20.
Very good. So the binomial probability formula. So each of these are binomial probabilities. So one way that you can do this is calculate each of these individual binomial probabilities from 20 to 32 and then add them all up. But that's a lot of work. That's 13 different probabilities that you have to calculate, and from a fairly complicated formula, and then add them all up. So when you find yourself doing that, adding up multiple binomial probabilities, most of the time you can use this shortcut. And the shortcut is normal approximation or fitting a bell curve onto the original binomial probability distribution. So all you would do is fit a bell curve, use continuity correction, and then find the areas of interest. So real quick, so that would mean you have this bell curve, and then at 20, so the data point of 20 really corresponds to a region of 0.5 in either direction, from 19.5 to 20.5. So this region denotes that one data point of just 20, but you want 20 or more, so that means everything to the right of that region as well. So this total shaded area is what you're trying to find when you're trying to find this probability. So then this goes back to just a regular z-score problem, where you just have to find the correct value for your z-score. So the z-score will be your data point, x. So this total right area that you're trying to find, where's the edge of it?
19.5.
Yeah, 19.5, so that's what you use for your z-score. So 19.5. And then how do you find the mean and standard deviation? Notice that it's not given to you explicitly.
The square root of NPQ.
Very good. So this turns out that this is a bell curve approximation onto the actual binomial probability distribution. So because it's a binomial probability distribution, the mean is NP and the standard deviation is the square root of NPQ. So this mean is NP, standard deviation is the square root of NPQ. So once you plug those in, you'll get the correct z-score. Once you get the z-score, look it up on the chart, and get the left area, and once you get the left area, subtract from 1 to get the right area. And that'll give you the same answer for this probability of passing had you added up all the probabilities from 20 to 32 using the binomial probability formula. Any questions? Okay, we ran over time. So that's it, guys. And so that was chapter 6, and chapter 7 was, we already reviewed that today, cognitive intervals. So study hard and feel free to email me with any questions you guys have. Before the test, yeah, not during.
You know why I said that. Last one, is everybody clear about how to get into the exam this time?
Yeah.